This is video 2 going through all of the hypothesis tests on HLAPS. And we're doing the last of the ones that make a claim against the population mean. And it's the Poisson. It's really nice because the Poisson always announces itself. So what's going on here is that Clara gets 1.5 good TSs per week. At least she did before lockdown. Now Crom comes along and says, I think it's getting worse in lockdown. Well, let's test that. So let's do it at the 5% level, and let's do it over a 10-week period. So this is a real classic Poisson. Already it's been extended. However, when we write the null and alternative hypothesis down, we do so based on the actual claim. So somebody has said, Crom has said that the average has gone down, so it's less than 1.5. And therefore the null hypothesis is that it's equal to 1.5. Remember that lambda is a traditional symbol for mean in the Poisson distribution, only in the Poisson distribution. It is a very similar idea to the population mean here. It's just that these numbers are Poisson numbers. So the population has got lots of noughts. Some weeks she didn't get a TS. Lots of ones. Sometimes you got 1, 2, 3, 4. And so you should think of this population as just a list of numbers listing all of the good TSs she got. She had a really great week that week. And it goes on, and in principle it's infinite. So we've made a claim against that. And so the first thing we must do, though, is extend it, because we're talking about a 10-week period, but this is still the null hypothesis. We're saying that we're expecting the variable to be 15 good TSs in a 10-week period. So now we go out and do the experiment. We'll have to wait 10 weeks for that. We do that and we come back, and let's say it was 8. Now you immediately say, oh yeah, that proves it. It has gone down. And they say, no, it doesn't prove it. If we look at these weeks here, she didn't get many good TSs here. So just the fact that she's got a low number isn't enough to prove it. We have to work out the probability, and we're working out, of course, the probability that the null hypothesis is correct. What are the chances that the null hypothesis is correct if we have 8 observed good TSs when we expected 15? Well, what we do now is quite subtle. Here is a Poisson 15 distribution. This is telling us the probability of Clara getting any number of good TSs in a 10-week period. So, for example, what are the chances that she gets 8 good TSs? That's this one here. It's pretty low, about 2%. And what are the chances she gets 13 good TSs? Is that one? About 8%. Of course, all of them are low because there are lots of options. Some are much more likely than others, but they're all low. Even the most likely thing is only 1%, 10%. So what we do is we say, what is the chances that Clara, that the null hypothesis is true based on 8 occurrences or less? And so we take a tail, 8 occurrences, about that lot there, and we say, what's the probability of what actually happened or worse happening? And we're going to add all of these probabilities up to get our p-value. And that's easily done. We go to distributions, Poisson, PCD, and we want to know what the probability of getting between none and 8 good TSs in a 10-week period is. And so we put the mean as 15, 0 to 8, run it, 3.74%, and we test that against the significance level. There we are. There's a separate video for binomial. So let's just look at the last one, bivariate. So this one, we have some data that is in the form of coordinates is probably the easiest way of thinking of it. So the population now, you should think of it as 1, 12 is one bit of data, 4, 54 is another, and there's an infinite number of these coordinates. So we can't really talk about mu, the average. We could talk about the average x coordinate or the average y coordinate. But what we're interested in a bivariate test is whether they're correlated or not. So the correlation coefficient is called R, correctly called Pearson's product moment correlation coefficient. And what we're interested in is whether that whether the population is correlated or not. Now, the population has several parameters. It has the average of the x coordinates, the average of the y coordinates, but it also has a correlation coefficient. Is the population correlated? Well, that is measured by rho, spelt like that, but written like that. That is the correlation coefficient of the population. Like mu, we don't know it. So all we can ever do is take a sample and estimate it. R is a unbiased estimator of rho, but notice my sample is pretty small. So what I'm asking is, and the only thing you'll ever be asked to do in an exam is say, is there correlation or not? And so the null and alternative hypothesis are these. They may ask it, the claim might be that there is a positive correlation, or it's simply saying whether it is correlated or not. So it is a claim made against a population parameter. It's just that this population parameter isn't a mean like it has been before. It is the correlation coefficient. So we just type it into the calculator and we get the two lists of data. In this one, list 2, and we go to test. It's a t-test, always will be for a bivariate one, because we don't know the sample, the population standard deviations. Now you may be tempted to press to sample here because it feels like there are 2 samples, but in fact there aren't, because this is a coordinate. It's really one thing. And anyway, this topic is called regression. It's another way of saying bivariate, regression. And there's so little to type in. In fact, all you type in is your alternative hypothesis. And it's built in that it's going to be against 0. So we're just saying, is there correlation or not? Or we're saying, is there a positive correlation or a negative correlation? In this case, it is there any correlation? And we just run it. So it's giving you lots of clues here. And you should write down a lot of these things on your answer. We can see the alternative hypothesis nicely written down. Rho is not equal to 0. Perfect. It reminds you to write rho instead of R, the population correlation coefficient, not the sample one, which is R. So you write down your p-value, 2.45%, and depending on the significance level, we'll accept or reject. I'll come back to 2 degrees of freedom. And there's quite a lot of other information. It tells you the equation of the regression line, which may be asked at some point in a question that has A, B, C in it. So maybe they'll ask that. But remember to go down and write down R. So R is 0.927. That's the correlation coefficient between these two in the sample. And write that down. Write down the t value and the p value, and you're done.